is the audio on? Is the audio working?
I can.
Okay, Fritz, can you hear us?
Yes, I can hear you.
Okay, thank you so much. And first of all, my sincere apologies for being delayed here. But of course, thank you a lot for making it online. And so welcome everybody to this afternoon's session of the fourth day of this workshop. And Fritz, maybe you can share your
I'm trying
screen.
to share my screen.
Yes, we can see your whole screen and in particular your slides.
Just a second.
Yeah. Yes.
Does that work?
Yes, we can see the slides. Would you mind switching it just for checking if everything works once?
Oh, yeah.
Yeah. Yeah, perfect. Thank you so much. Okay, so now we're finally ready. So again, it's a very big pleasure to have Professor Fritz Gesztesy here from Baylor. And he's going to talk about the essential self-adjointness for a class of pseudo-differential operators perturbed by strongly singular potential coefficients. So Fritz, the floor is yours.
Thank you very much. In fact, I want to start by thanking all organizers for the kind invitation to speak, and especially Raphael, who offered this idea of an online talk. So I decided to speak about two classical topics, essential self-adjointness, needs no introduction in quantum mechanics, and perturbations by strongly singular potential coefficients. So as you can see from the first slide, this is joint work with two of my colleagues here at Baylor, Markus Hunziker and Dorina Mitria, and the ODE part of this talk is also jointly with Gerald Deschel in Vienna. So here's the motivation and some of the topics that will be discussed. So, as I said already, we would like to prove essential self-adjointness for strongly singular homogeneous differential operators, and also include a certain class of pseudo-differential operators perturbed by strongly singular homogeneous potential coefficients. And so we will start with singular ODEs on the half-line, then turn to singular PDE examples on Rn and the origin removed. Finally, we will look at essential self-adjointness of fractional powers of the Laplacian on C0 infinity of Rn minus x, where x is a discrete subset of Rn. And at the very end, we're going to perturb these fractional powers of Laplacian with strongly singular homogeneous potential coefficients. So here's a typical example of a homogeneous but strongly singular second order ODE operator on the half-line. It's the Bessel operator. So everybody has seen this. It's Laplacian plus constant over x squared. So this is homogeneous. And more generally, one would look into if one does a one potential coefficient, and this is what I will focus on, one would look at the 2mth second derivative plus c over x to the 2m, again on C0 infinity of the non-negative, actually the positive half-line. So in the following, whenever you see this letter m, it counts powers of the Laplacian. So the PDE operators we will look at are very similar, so they are analogous to what you just saw in the ODE case. You look at powers of the Laplacian, integer powers at first. Later on, there will be fractional powers. And then you perturb by constant over mod x to the 2m. So again, homogeneous, strongly singular. And eventually, we'll change the integer power m into a fractional power s. And we'll also consider this discrete subset x. So this is a a set in Rn with no finite accumulation point. And eventually we would like to know whether minus Laplacian to the s plus c over x to the minus 2s is essentially self-adjoint or not on C0 infinity of Rn minus the origin or Rn minus this discrete set x. Now, in the end, we are not quite there yet. We would like to do a more general problem, and you can see that from the last two lines. So we would like to add infinitely many strongly singular potential coefficients. Xj here runs through this discrete set x. That's a difficult problem, and at this point I don't have too many results about that yet, but a little earlier this part here will be completely analyzed, and we will get criteria, so if and only if conditions for essential self-adjointness. All right, let me start with the ODE part of this talk. So again, we are mth order, one homogeneous singular potential coefficient, constant over x to the 2m. And again, the question is, when would this be essentially self-adjoint on, say, C0 infinity of the open half-line? Now, before I go into results, let me mention a few reductions of this problem. So first of all, essential self-adjointness boils down to these differential operators on C0 infinity of 0, the open interval 0 infinity, whether these differential operators are limit point at both endpoints, so x equals 0 and x equals infinity. But it turns out infinity is absolutely trivial because everything's bounded there. The potential coefficient 6 over x to the 2m even goes to 0. So infinity is never an issue. All one has to do is focus on the singular point x equals 0. So this is step number one. Then, in order to see whether one is essentially self-adjoint or not, so in other words, whether one is in the limit point case at x equals 0 or not, it suffices to look at solutions of the differential equation. So tau, the differential expression on y, is a multiple of y. The multiple mu here plus minus is a complex number in the open upper or lower half plane. And the point is your limit point at 0 and therefore essentially self-adjoint on this set C0 infinity of the open interval 0 infinity, if and only if you have exactly half of the solutions in L2 near 0 and the other half, of course, not. So exactly half of the solutions of such a differential expression or differential equation here should be in L2. Actually, only locally. So we don't worry about infinity. We just worry about a neighborhood of the singular point x equals 0. Then it turns out, this is a further highly non-trivial simplification, we don't need to worry about this spectral parameter mu, this complex parameter mu at all. In fact, any parameter one can show is equivalent to any other. So of course, then you choose the far simplest one, mu equals 0, in which case this differential equation has very elementary solutions in terms of powers, and possibly powers times powers of logarithms. So this is going back to classical results by Frobenius, Fuchs, and Sauvage. And let me also mention there is a characteristic equation or characteristic determinant, sometimes called the initial equation in the study of ordinary differential equations in the complex domain. And in our case, it is very simple because we are homogeneous and of order 2m. You see in blue this kind of discriminant d2m, and its zeros will play a crucial role. In fact, its zeros will be the exponents of the powers of solutions. And so these zeros of D2M will determine whether we have half of the solutions in L2 or not, and so whether we are essentially self-adjoint or not. Now, what I will do is, without loss of generality, because there is continuity with respect to the parameter C. Remember, C over x to the 2m was our potential coefficient. So we are continuous in C, and therefore we can, without loss of generality, order the real parts of these solutions of D2m equals 0. And we order them in magnitude, so alpha 1 has the smallest real part, and so on. We will always do this from now on. Now, again, why did I focus on the zeros of this discriminant? Well, because you can see here the solutions are essentially given by constant times x to these alpha j's, and the alpha j's are the zeros of the discriminant that I just showed you. Sometimes, in the non-generic case, you might also have powers of logarithms, so a polynomial of log x. However, when it comes to L2 characterizations, the logarithms are irrelevant, and so we can ignore them. So, looking at the solution, yj being a multiple of x to the alpha j of c, you see that you are in L2 or not if and only if the real part of these zeros is larger or less than a half. In fact, less or equal to a half will give you non-L2 membership. Strictly larger than minus a half will give you L2 membership. And remember, we want exactly half of these alphas to be on one side of minus a half and the other half on the other side, including minus a half. So let's move on to trying to analyze these zeros alpha j, whose real part decides whether we are L2 or not, and so whether we have the limit point situation or not. One can compute the asymptotic behavior as c goes to plus or minus infinity. I've mentioned this here. This is not something you need to recall later on. I just have it here for completeness. I should also say, we said the crucial property here is whether the real part of alpha j is larger or less than a half, sorry, minus a half. And minus a half included when you do not want to be in L2. You are L2 if and only if the real part is strictly larger than minus a half. This reminds of stability theory for ODE systems, where Routh-Hurwitz criteria are used. Typically, you have eigenvalues of a particular matrix, whose the eigenvalues are sometimes called characteristic exponents, and you have stability typically when all the eigenvalues have either negative or positive real parts. So in our case, it's not 0, but minus a half that is the dividing line. So this is a familiar topic from stability theory of differential systems. In this particular case that I showed you, there is an underlying Hurwitz matrix, and its determinant plays a role. I'm not going to dwell too much on this. I just wanted to show the structure of this matrix is rather peculiar. All the entries are rational numbers. This is because we had this very special discriminant D2m. All right, so let me introduce a notation that is convenient in our context, namely we sorry, I hit the wrong button here. Yes, so we want to denote by the number of tau mc the number of j's such that the real part of c is larger than minus a half. So again, strictly larger than minus a half. So these are the L2 solutions near x equals 0. And again, in order to be essentially self-adjoint, we want exactly half of them, so m, to be in this situation with real part strictly larger than a half, than minus a half. So I will use the floor and ceiling notation. This is all standard, so let me move on to that. and start with the very simplest case of the Bessel operator. So when m is 1, you have a second order differential expression, minus d2 by dx squared plus constant over x squared. And everyone remembers that this is essentially self-adjoint on C0 infinity of the positive half line if and only if C is larger or equal to 3/4. Whenever C is less than 3/4, you are not essentially self-adjoint. Now, when you go to higher m, so higher order situations, the situation becomes complex very quickly. So m larger or equal to 2 is considerably more involved. So we have done a very careful Routh-Hurwitz consideration, and there are a number of C's involved here that one can find, but the most important for us is what I call Cm superscript m. This is the one that will decide whether we are essentially self-adjoint or not. And in terms of this Routh-Hurwitz characterization, this number of L2 solutions with alphas that are strictly larger than minus a half satisfies what is written here. So you see m plus 1, m plus 2k plus 1, 2m, and so on. But the only interesting one for us is the very first one in red. You get m solutions if and only if your constant c, so the c over x to the 2m, the potential coefficient, if c is larger or equal to this largest of these numbers, cmm, and this answers our question in the following sense. Before I actually give you the precise answer, let me just say these numbers grow very quickly, and I have a lower bound here for them. But let me say the following here. So for any m, you can find a constant, which is the CMM that we just looked at, so that the number of L2 solutions, so in other words, the number of alpha j's whose real part was strictly larger than minus a half is precisely m, and the value of this, so the set of c's for which this is true, turns out to be this half line from Cm or CMM all the way to infinity. And so in other words, our 2mth order homogeneous, strongly singular differential operators, here they are, minus 1 to the m, d2 by d2m by dx to the 2m plus c times x to the minus 2m on c0 infinity, the open interval 0 infinity, is essentially self-adjoint in L2 with Lebesgue measure. If I don't write a measure, it's always Lebesgue measure, if and only if this constant c, the coupling constant, is larger than this number Cm whose existence one can prove. Now, again, the first Cn is 3/4. We just saw the Bessel case, so this is the Bessel case. The others have this lower bound, and so what this says is an interesting property here, namely, there are no islands in C of non-self-adjointness. So it's a half line from minus infinity to Cm. You are not, in the open interval there, you are not essentially self-adjoint, but as soon as you are Cm or larger, you are essentially self-adjoint. So you cannot have a situation where you are self-adjoint, essentially self-adjoint for an interval, then there is a gap, you're not essentially self-adjoint, then you're essentially self-adjoint again, and so on. This cannot happen in this simple case of a one-point potential perturbation, homogeneous singular perturbation of the second order derivative. You will see this property of no islands is not true in the PDE context. It's an artifact of our ODE situation that we are looking at. So here I have a few more of these numbers for you. Once again, the first one is, of course, the Bessel operator. C1 is 3/4. For the fourth order operator, for C2, it jumps from 3/4 to 45. And then it grows very, very rapidly. And of course, since we are looking at zeros of a polynomial, we are running into the problem of the quintic. And so you can give the first four explicitly, and then you can numerically approximate those numbers Cm. Okay, so at this point, we're going to make the transition to PDE operators. So powers, in this case at the moment, integer powers of the Laplacian, and then we perturb again by a homogeneous potential coefficient. And the question then is such a polyharmonic operator essentially self-adjoint on C0 infinity of Rn minus the origin? Now, since we are spherically symmetric, you can do a standard separation of variables argument and reduce this to an infinite family of ODE operators, singular ODE operators, which are written here. They are called tau m and L. So L here runs from 0 to infinity. This is the angular momentum. And m is the power of the Laplacian, and n is the dimension of the space. Again, you get a discriminant, if you want, dmnl in this context, which is a polynomial of degree 2m. Its zeros will be crucial, as you will see in a minute. So here's the actual structure now in this PDE context of the analog of the D2M, this discriminant that we had in the ODE case. And let me just repeat here that tau m and L, these are the reduced ODE operators, are essentially self-adjoint in L2, if and only if exactly half of their roots of dm have real part less or equal to minus a half, and then the other, these are the L2 solutions, would have real part strictly larger than minus a half. So the same technique we applied in the ODE case can be applied here in the PDE context, because we reduce it to an infinite direct sum of ODE operators. So once again, we will call the zeros of D alpha, and again, by continuity, we will order them with respect to their real parts, so that alpha 1 has the smallest one, and so on. One knows asymptotics of these real parts as c goes to plus or minus infinity, as in the ODE case. So I have written one of these relations here on the bottom. And here is this is a little more involved. I'm not going to go too much into this. Let me just say again, the dividing line for us is minus a half in terms of the real part of the alphas. So we're going to look at the maximum, called gamma MNL, of the real part, the maximum of all the values of C, the coupling constant, so that the real part is minus a half. Remember, this minus a half is the dividing line. And so if C is larger or equal to this gamma MNL, then we are essentially self-adjoint. In fact, it turns out when m is between 1 and 3, this is an if and only if statement, not just an if statement. Again, one can analyze the discriminant. It's related to another Hurwitz matrix. I leave out the details of that Hurwitz matrix, and let's immediately go to special cases. So the simplest case in this integer power situation is, of course, m equals 1, just the Laplacian itself, perturbed by constant over mod x squared. Well, you do the angular momentum decomposition, you get this tau and L, and here they are. So this is well known, of course, from n-dimensional quantum mechanics, if you want. And the simplest one is, again, our Bessel operator that we had in the ODE case repeatedly. And so, no surprise, tau 1, the first of these, is essentially self-adjoint if and only if C1 is again larger or equal to this number 3/4. Now, if we look at all, so if we look at the entire family of tau and L, then we realize that this 3/4 criterion is going to give us the following criterion for C. So T1 minus Laplacian plus C over mod x squared, defined on C0 infinity of Rn minus the origin, is essentially self-adjoint in L2 of Rn if and only if, so again, this is a criterion, this constant C, the coupling constant, is larger or equal to minus n times n minus 4 over 4. So this is what happens when you analyze this three-quarter situation from the ODE problems. Now, you can do a special case. Suppose C is 0, then there is no potential, just a Laplacian defined on C0 infinity of Rn minus the origin. And in that case, you have essential self-adjointness if and only if the dimension is at least equal to 4. Now, everything on this page is, of course, well known. So this is a absolutely classical result in this area. But that was just the simplest case, m equals 1, so just the power 1 of the Laplacian. So let's have a look at the power m equals 2. Well, now it's a fourth order, strongly singular object, so Laplacian squared, and then plus c over mod x to the power 4, again defined on the same space, C0 infinity of Rn minus the origin. You analyze now the corresponding family, infinite family of ODE operators. It's also fourth order, of course. It's a second order squared plus c over r to the fourth. In this context, it helps actually, so for m equals 2, to look at a closely related family, tau 2, that is fourth order, but contains two parameters, C1 and C2. So you see the C2 is the constant over r to the fourth. This is what we normally focus on. And there's also a C1 that has a second order derivative with 1 over r squared term. So again, homogeneous, symmetric, and so on. And in this context for tau 2, when you look at powers r to the z, you get multiples of r to the z minus 4, and d2 is now the analog of our discriminant. It's a quartic polynomial, so here it is explicitly in terms of c1 and c2. And again, it's zeros, and the real part of the zeros is what determines essential self-adjointness. And so I have, for once more, I wrote down a Hurwitz matrix that is related to this discriminant D2. But let me just focus on essential self-adjointness here in L2 on the positive half-line. This tau 2, C1, C2 is essentially self-adjoint on C0 infinity of the open interval 0 infinity, if and only if C1 is larger or equal to 11 over 4, then C2 needs to be larger than this expression. If C1 is less than 11 over 4, then, well, C2 needs to be larger or equal to this expression. Now, in our context, why did we study tau 2 of C1 and C2? Well, because for this choice of C2 and this choice of C1, tau 2 becomes our tau 2 and L, so the direct sum over these differential expressions was what we got after angular momentum decomposition. So now we can analyze this using the result for tau 2. And we actually, going back to this gamma 2 and L's, one realizes that tau, the differential expressions you get after angular momentum decomposition, so L here runs from 0 to infinity, are essentially self-adjoint in L2 if and only if C is larger or equal to these gammas. The gammas can be computed in this case, so it's not pretty, but it's explicit. The only important one is gamma 2 and 0, as it turns out, because all the higher L's are less than that. And so, long story short, here is the result for the fourth order case, so Laplacian squared plus c over x to the minus 4 on C0 infinity of Rn minus 0. This operator is essentially self-adjoint in L2 of Rn if and only if the constant c satisfies these inequalities depending on dimension. That is not so well known. In fact, I don't know literature about this, so may well exist, but it's not known to me. Anyway, there's an interesting special case again. Suppose C is 0, so you don't have this singular perturbation term. You can ask when is minus Laplacian squared defined on C0 infinity of Rn minus 0 essentially self-adjoint in L2? And the answer is, if and only if, the dimension is larger or equal to 8. So you see it was 4 for T1, it's 8 for T2. Well, it's of course multiples of 4 for higher m's. So the answer is always m times 4. Now let me just give you the answer for m equals 3. I won't give you any more details here. It gets a little wild. Anyway, this is now 6th order. And again, you have an if and only if statement, so a criterion for essentially self-adjointness of this T3 in L2 of Rn, given these inequalities for C. Once more, you can of course ask what happens when C is 0, and the answer now is 12. So it's 3 times 4. All right. Let me mention one example that's a little deflating. So far we had, in fact, no islands of non-essential self-adjointness. Let me show you an example, a counterexample to this. So this is not as simple as in the ODE situation I started with. Let me do an example where the power m is 5, the space dimension is 20. Then it turns out that the answer to this question here, namely, is there always a CMN so that TMC is essentially self-adjoint on that half line from CMN all the way to infinity? The answer is no. And the counterexample is the one with m equals 5 and n equals 20. So in 20 dimensions, we were able to see that you actually have a situation where you are essentially self-adjoint on a compact interval, and then another half line with a non-trivial gap from beta to gamma in between. So self-adjoint here, essentially self-adjoint there, but not essentially self-adjoint for the gap from gamma, from beta to gamma. And beta and gamma are definitely different numbers. So the gap is non-trivial. All right, so now I'm going to make the jump from integer powers to fractional powers. So what we want to establish eventually is we have a fractional power of the Laplacian, so the fractional power is denoted by S, and we define it on C0 infinity of Rn minus, for instance, the origin, or more generally, a discrete set X. So again, a set that's non-empty and has no finite limit points. I'm saying non-empty because if X is empty, the statement is elementary, then it's always true that you are essentially self-adjoint. So there are some facts here about Sobolev spaces. I won't pay too much attention to this right now, but what I want to point your attention to is an interesting statement about, sorry about this, about distributions with point-like support, if you want. So again, suppose you have a distribution U in D prime that has support contained in a discrete set. Now, if the discrete set is just one point, we all know that a one-point supported distribution is a linear combination of the delta distribution and its derivatives. You might ask, what happens if you have more than one point? Finitely many, or even infinitely many, and in our case here, a discrete set. And the answer is not much changes. The result is still true that your distribution is a linear combination of derivatives of distributions supported at the points in your discrete set X. So let me leave this for a moment and use it in a second. So here's a non-trivial result about dense sets in fractional Sobolev spaces. Again, X is a non-empty discrete subset of Rn. Our S here is at the moment a real parameter. And I'm interested in what is dense in HS. And it turns out that the set C0 infinity of Rn minus that discrete set X is dense in HS if and only if S is in a certain half, on a certain half line. So minus infinity to n over 2, n the space dimension, n over 2 included. In order to prove this, we are using what I just showed you, this representation of distributions in D prime with support in a discrete set. So let me go back to what we really want to do. We want to show essential self-adjointness of fractional powers of the Laplacian, or slightly generalized versions, minus Laplacian plus m squared to some fractional power on C0 infinity of Rn minus a discrete set. So for instance, this is not totally academic here. When S is a half, you get what's sometimes called a pseudo-relativistic operator, and there is some meaning behind this. In fact, when you look at Dirac operators, at least free Dirac operators, they are related to square roots of this form. And in any case, these are the models for or maybe the prime motivation for trying to understand essential self-adjointness for such operators. So what we will do is we will use the graph of this self-adjoint operator minus Laplacian, and I will focus on the first version for simplicity, although everything I'm telling you will work for this operator as well. So we will focus on the graph, Hilbert space associated with this operator, and then show that that graph, Hilbert space, is topologically equivalent to the fractional Sobolev space H2S. And that will be a way for us to determine domains of essential self-adjointness. So let's move on for a moment. So again, this is totally standard. So we have a linear operator T in Hilbert space H. We look at its graph. We introduce the usual scalar product and norm. And the use of all this is, of course, that the operator T is closed if and only if the graph with that scalar product that is introduced here is in fact complete or is a Hilbert space. So this is the reason why I'm looking at graphs. And I should also say that domains of essential self-adjointness, sometimes called cores, are also characterized by that when you have an element V in the domain of your operator that's perpendicular in terms of the graph Hilbert space to a set D, then V being 0 is equivalent to D being a core, so a domain of essential self-adjointness for T. And so that actually is a very convenient criterion to test essential self-adjointness. And we will apply this now in the case of the fractional power of a Laplacian. Now, by Fourier transform, these operators are unitarily equivalent to multiplication by the by mod xi to the 2s, or mod xi squared plus m squared to the s in these two cases. So because of this being maximally defined multiplication operators by a real valued function, these operators are, of course, self-adjoint. Now, I want to describe cores, so domains of essential self-adjointness for these objects. And I will employ this criterion star to get there. So before I do this, let me just remind you of the uh, graph Hilbert space. So this is denoted by H, and the fractional power of the Laplacian is my operator T now. And so that space turns out to be the fractional Sobolev space with scalar product induced by the graph Hilbert space. It's written here. But in fact, since you have these obvious inequalities written down here for finite numbers and non-zero numbers C1 and C2, it is indeed true what I said a little earlier, that the graph Hilbert space of the fractional power of the Laplacian and these fractional Sobolev spaces, H2S, are equivalent. So their topologies are equivalent. And we will use that. So when we are dense, so in other words, if I want a core for my fractional power of the Laplacian minus Laplacian to the S, all I need is dense subspaces of H2S. And so indeed, we concluded that linear subspace D is a core for minus Laplacian to the S, equivalently a domain of essential self-adjointness, if and only if D is dense in the fractional Sobolev space H2S. Well, remember we had a denseness result for these Sobolev spaces. I mentioned that just a minute or two earlier. And so sure enough, here we have minus Laplacian to the S restricted to C0 infinity of Rn minus a discrete set is essentially self-adjoint in L2 if and only if the space dimension is larger or equal to 4 times S. You see, this is the 4 times M that we had for the integer powers, but now it's proven for fractional powers. So in the very last few pages, this will be done quickly. I want to apply Kato-Rehlich-Wüst type perturbation theory. So relative boundedness with bound equal to 1. And I will combine that with fractional higher order Hardy-Rehlich-Biermann inequalities to get a result for a strongly singular perturbation of the fractional Laplacian. Again, a homogeneous perturbation. So here is the Kato-Rehlich-Wüst result. Again, you have a B, a symmetric operator with domain larger than A self-adjoint, and you have B is relatively bounded with bound 1 with respect to A. Then we know that A plus CB, where C is anything in the closed interval minus 1, 1, is essentially self-adjoint on the domain of A or any operator core. So any domain of essential self-adjointness for A. Now, in the open interval, so when the bound is less than 1, so to speak, then of course you're self-adjoint. Now, how do I apply this? Well, first of all, my A will be the fractional Laplacian. My B will be mod xi to the minus 2s, so a homogeneous fractional power. And my Kato-Rehlich-Wüst inequality turns out to be the fractional higher order Biermann-Hardy-Rehlich type inequality, which is known in this form with an optimal constant on the left-hand side. So in other words, we can determine precisely when the operator bound that we are seeking of mod xi to the minus 2s is less or equal to 1. Here's the one of the bound with respect to the fractional power of the Laplacian. And so applying this inequality, which you can interpret as a Kato-Rehlich-Wüst inequality, you get the following statement for strongly singular perturbations, mod x to the minus 2s, if you want, of minus Laplacian to the s, which says that this object on H2s, or any core of it, so for instance, C0 infinity of Rn minus a discrete set, is essentially self-adjoint in L2 if C is in the closed interval minus 1, 1. Notice I don't have an if and only if here. No, I'm using perturbation theory. So I get an if statement. I do not get an if and only if statement here. Still, it's a nice result because it gives you a, uh, uh, a large class of homogeneous, strongly singular perturbations of the fractional Laplacian for which you are essentially self-adjoint under these conditions or actually self-adjoint under, under this condition. Now, one can actually see that the condition on S that we had in our theorem is optimal. The condition on Z, of course, as I just said, is perturbation theory. That one is not optimal. And with that, I'm going to show you a few references that are relevant in this context. And most importantly, happy birthday, Volker. Thank you very much.
Thank you very much, Fritz, for this very nice talk. It definitely opens, I think, new doors for spectral and scattering theory involving such operators, in particular the difficult polyharmonic operator. All right, time for questions. And then if you have a question, I ask you to maybe say your name because Fritz might not see who you are.
Hello, Fritz. This is Rafael.
I can see you actually. I can see the audience.
Okay. Fritz, you were talking about islands where of seas where there is not essential self-adjointness. I wonder if there is the possibility of other sets, like for example, Cantor sets,
Oh,
sets, where you do not have essential self-adjointness.
so let me say, my honest answer is I don't know. We were, of course, from the ODE situation, we were expecting a half line. And we were quite surprised to find this island, so a gap in essential self-adjointness. I don't know. I haven't really given it much thought to have a meaningful answer to your question. I think this is a non-trivial question. I don't know. That's the honest answer.
Okay, Fritz, thank you very much, Fritz.
Yeah, first of all, thank you, Fritz, for joining us here, and thank you for your wishes. I really appreciate that. This is Volker speaking. So my question actually relates to the last slide you presented, the case you would like to treat. That really looks interesting. I mean, one would expect that if there is an accumulation point for the set xj, that it becomes very subtle to decide.
Okay, so since we are discrete, the only accumulation points can be at infinity. But even that is, of course, non-trivial. So there are no finite accumulation points because I mean, if you have a finite accumulation point, I really don't know how to address this problem. This is, I think this is a difficult thing. And there are no known techniques to me in this case. But even if, even finitely many of these points xj, this is not trivial. I mean, you can, of course, by brute force, do a perturbation theory analysis and then restrict the magnitude of your CJs appropriately. But that's not what I have in mind. I have in mind that different xj's should not interfere with each other. So in other words, the bound that I get from perturbation theory for one center should be the same for the CJs for all of these centers. And so far, we have not been able to prove that. If I have integer powers, I could prove that. Because then you use appropriate partitions of unity. And since you know how to commute them through a integer power of the Laplacian, when you get as perturbation lower order terms, those you can handle. But you see, minus Laplacian to the s when s is not an integer is a non-local operator. And it's a singular integral operator, to be precise. And you cannot so simply commute a partition of unity that focuses on each of these xj's, so it's concentrated around the xj's. You cannot commute that through the Laplacian to the s. And so far, that has been a real stumbling block.
Thank you. Are there any further questions? Yeah, I think so. This many particle polyharmonic operator would be very interesting to study also for, in particular, Hardy type inequalities. But may I ask two less deep questions? So first of all, on your 17th slide, I think it was the first time you went back to Rn from the half line, basically. And from then on, I think it was always this number n plus 2l appearing. Is this sort of, can this be thought of as an effective parameter, like an effective dimension maybe?
Oh, so where exactly do we have that?
Everywhere, actually. So here in
oh. So the crucial part here, this is asymptotics, of course, yes. But the crucial part is not the m. The crucial part is minus a half. That really is what's deciding between L2 or not L2 behavior. Let me go back to a page where we can see this explicitly. Here we are. You see, the solutions are of this form. And you are L2 near zero if alpha j, or the real part of alpha j, is larger or equal to minus a half. And so minus a half is the crucial point here. If you are less or equal to minus a half, you're not L2. But if you're larger, strictly larger, you're L2. And in the end, I want m of these that are larger than L2, and the other m should be less or equal to minus a half. So it's always, so this is the criterion, the most important one for membership in L2 or not. This m minus a half, this was an asymptotic, this is an asymptotic result. When C gets large.
My voice might not have been clear. I mean Norbert, not Martha, but Norbert. N, the spatial dimension plus twice the angular momentum. This was something that occurred, I think.
Let's see where we can find that.
On slide 17.
Maybe here?
Yeah, also there. So for instance, in this second displayed formula, tau 1 NL, you see in this first line n plus 2l appearing in both of these fractions, and I think
yes. So
this appears everywhere, right?
This is actually the usual way one writes this is the second line here. The L times L plus dimension minus 2, right? This is what people will recognize. I wrote it in two ways that there's some reason for this, but this is the standard angular momentum decomposition of the Laplacian. And so I should say that L times L plus n minus 2 are the eigenvalues of the Laplace-Beltrami operator that you get when you do spherical symmetry here. So in other words, you write your T1 is a ODE operator, tensor product with 1 plus the Laplace-Beltrami multiplied by 1 over r squared when you do the angular momentum decomposition. And L times L plus n minus 2 is indeed, these are the eigenvalues of the Laplace-Beltrami on the sphere.
And then the second very quick
question. Sphere is n minus 1.
Okay. And then thank you. And the second, very brief question, do you have explicit expressions for the resolvent or powers of the resolvent of these polyharmonic operators? For the kernel of
so for the polyharmonic ones, no, but in part because we didn't look for them. So certainly for T1, so in the ODE context, our tau 1 is still on this page here. One can write down the Green's function, and therefore the resolvent explicitly. For higher order operators, there are prescriptions on how to get the Green's function. So one could do it, but the complexity increases very quickly with M.
Okay, thank you very much. Are there any further questions, remarks? Well, if that's not the case, thank you a lot, Fritz from Merida.
Thank you very much.